I don't even know who the science fiction writers nowadays are. I don't read that stuff anymore. But when I was growing up, Isaac Asimov was. Anybody heard of that name? Mm-hmm.
Like as a multivax story, multivax, story.
Oh no, I haven't read that. Yeah, I forget the book. So anyway, he talks about spaceships like this. Okay, so a space station consists of a giant rotating hollow cylinder of mass 10 to the million kg. And now see, with Elon Musk's rocket, all this is possible. Before reusable rockets, all this was just science fiction, but now you can actually do it. Including people on the station and a radius of 100 meters. It's rotating in space at 3.3 revolutions per minute. So here's the cylinder. To produce artificial gravity. If 100 people of average mass 65 kg spacewalk to an awaiting spaceship, what is the new rotation rate when all the people are off the station? Okay, so so you had 100 people on the space station. I'm not going to draw all 100 people, and they get onto a space station and they leave. So what will happen? Now this will rotate faster. Okay. So the space station will rotate faster. All right. Let's. The problem doesn't ask us this. Let's calculate this acceleration, centripetal acceleration. Let's see if this corresponds to g. Is r omega square. That's what it's related. Okay. Omega is again. This is an aside. Omega is 3.3 revolutions per minute. It's equal to 3.3 into 2 pi radians divided by 60 seconds. And centripetal acceleration is r omega square, 100 meters times 0.35 radians per second square. This thing is rotating too fast. Okay, so this is not for Earthlings. This is some other beings. They're used to 3 times the gravity, 3g. Yep. All right.
That makes them pretty heavy, right?
Strong boned. Their bones would be much stronger than ours.
Would that, and if they were denser, would that make them heavier?
Yeah. So these guys are all. And on this planet, you wouldn't want to grow too big.
So. No, you won't look it, man.
Mm-hmm. All right, so again, so in this problem, now back to the problem. So this was a side. Now back to the problem. L initial is equal to L final.
I think you forgot the square.
Oh, there you go. This didn't make sense, did it? See, everything makes sense. No, everything has to make sense. So 12.25 meters per second. Okay, maybe this is designed for Earthlings. Okay, slightly lower. So you want to reduce it by at least 10%, 20%. So you would be rotating at 2.7 revolutions per minute to get G. Okay. Anyway. All right. So in this problem, again, angular momentum is conserved. This is the initial angular momentum with all these people on board, and then they fly away in some spacecraft, and the final angular momentum should be the same. So this is spinning faster now. Okay. So Li equal to L final, I initial. Okay, I'm going to rush through this. This is the moment of inertia of the cylinder. The cylinder is it's a hollow cylinder, so all of the mass is at the edge. All of the masses at distance r, and so there is the moment of inertia of the cylinder. Okay, and then here's 100 people, mass of each person times r squared. They're also all at the rim. Okay, so that's the initial moment of inertia, and the final moment of inertia is what's the final moment of inertia? Just mr squared, just for the spacecraft. Those people have left. Okay. So 10 to the 6 kgs times 100 meters square plus 100 times 65 kg times 100 meters square. So this is 10 to the 10 plus, that's 468 468.0065 into 10 to the power 10 kg meters square. The reason I wrote it like this is, you see, they walk away, you won't even miss them. It's contributing nothing to the moment of inertia to the spaceship. Okay, 0.006, 0.6%. And so that's what the space station will speed up by. Its angular velocity will increase by 0.6%. Okay. I final is just mr square equal to 10 to the power 10 kg meter per square. And omega final is I initial or I final as promised. See, the angular speed increased by, if you multiply this guy by 100, that's 0.65%. Okay, so it's sped up by that much. Yep. We have changed the problem. How's that? Okay, so a space station consists of a giant, including people, okay? And so Angie is right, but we have changed the problem. Now, when you guys write your physics book, you see, you would write it where the spaceship was 1,000,000 kg and then you add on the mass of the people. You guys understand? So, design of a good problem. Okay. Okay, guys, I will see some of you guys in lab. Okay.